Alright, in today's video we're going to practice some basic equilibrium problems for grade 12 chemistry. They'll range in difficulty from problems that don't involve any algebra, problems with no ice tables, problem with ice tables, and then we'll do some problems with algebra as well. We'll use the graphing calculator as well as algebra to solve those problems later on. So this first your best bet, by the way, is to not just watch the video, but to pause and try the problems yourself, and then check your answers as we go. If you're in my class, be sure that you're paying attention to the level of detail in your answers. That's what I expect on tests and on the exam. So question number 1 says you've got half a mole of ammonia gas put into a 10-liter flask at a given temperature. It decomposes into nitrogen, hydrogen, and at equilibrium 5.2 grams of nitrogen is discovered in the flask. Part A, calculate the equilibrium constant Kc for the reaction above at the temperature for the experiment. So you read that question and a few things jump out at you. The first is moles and volume. So moles and volume, we know that we're going to convert that to molarity, and to do that we're going to use the formula C equals N divided by V. Moles divided by liters gives us concentration, molarity. We can also tell that because the ammonia given was placed into the flask, that's the initial concentration of the ammonia that we're going to calculate. When equilibrium is established, that phrase is talking not about the initial conditions, but the equilibrium conditions in the container. So since we have initial and equilibrium conditions given, that's a signal that we're going to need to set up that ice table to solve the problem. So I'm going to write my balanced equation down. So 2 NH3s decompose to make nitrogen and 3 hydrogens. These are all gases in the question, so this is a homogeneous equilibrium, homogeneous, and because everything is in the gas phase, homogeneous, or all same phase, they're all going to be included in the Kc expression. So the first thing I'll do is I'll find the initial concentration of the ammonia, moles divided by volume, so 0.50 moles divided by 10.0 liters. We grab a calculator if we have to, or just do some mental math. We're only going to keep 2 significant digits. 0.50 has 2 digits, and 10.0 has 3 digits. So that's going to be 0.050 molarity. In my ICE table, ICE, the I stands for the initial conditions, the C is the equilibrium change, and the E at the end is the equilibrium conditions in the container. So this 0.050 is the initial 0.050 molarity, the initial ammonia concentration. Nothing else was placed in the container, so the initial nitrogen and the initial hydrogen will both be 0 to begin with. Now, 5.2 grams of nitrogen was discovered when equilibrium was reached. So we have to take the grams of nitrogen and switch it to moles. So to do that, we can use the formula moles equals mass divided by molar mass. The mass, 5.2 grams. The molar mass from a periodic table, 2 times 14.01 will be 28.02. Once we have the moles, we'll then again divide by volume to get concentration. Alternatively, you could set up 2 unit multipliers to do this, and that's what I'll do here. So the equilibrium concentration of nitrogen will be, I'll take my 5.2 grams of nitrogen, and with 1 unit multiplier, I'll switch grams to moles of nitrogen, and then with a second one, I'll take my moles and just divide by the liters. So on top will just be a 1, on the bottom will be the liters. Moles divided by liters is molarity. So 1 mole of nitrogen weighs 28.02 grams, and then the volume was 10.0 liters. Now if you look at what I'm doing with the unit multipliers, I'm doing the same thing someone would have done with these formulas. The mass divided by the molar mass, 5.2 divided by 28.02, then dividing by the volume. So 5.2 divided by 28.02 divided by 10, keeping two significant digits again, and this is the nitrogen concentration. So we go to the nitrogen column, and at equilibrium, its concentration is 0.019 molarity. Okay? Now, what do we do next? Well, we can see in this table that we have all of the initial conditions, and we have one other number. Whenever you see that, you know that you're able to fill in the entire table. We look at the nitrogen column first because we have two of the three numbers there. It started with 0 and it finished with 0.019. So since it started with 0, it must have gained 0.019 molarity. Now, the other changes we can deduce from the stoichiometry in the balanced equation. We look at the ratios there. So there's a 3-to-1 ratio, hydrogen to nitrogen. So if the nitrogen gained 0.019, the hydrogen must gain 3 times as much, 3-to-1. So 3 times 0.019 gives me 0.057. Since the hydrogen began with nothing, it gained this amount, it ends with 0.057 molarity. Now the ammonia ratio is 2 for every 1 nitrogen, 2 moles ammonia for every 1 mole of nitrogen. So if the nitrogen gained 0.019, the ammonia is on the other side of the equation. It's a reactant where the nitrogen was a product. So because it's on the other side, it's not going to gain, it's going to lose. Everything on one side of the equation does one thing, in this case, everything on the right gained, and everything on the other side of the equation does the opposite. So in this case, it loses. It will not always be the case that the left loses and the right adds. Sometimes it's reversed. When the right-hand side is gaining like this, it means that the reaction is headed in the forward direction. You're creating these products. In order to create those products, you have to use up reactants. That's why the ammonia decreases as it's changed. So that ratio 2-to-1 means it's going to lose twice as much as the nitrogen had gained. So 2 times 0.019 gives me 0.038 molarity. So now 0.05 is what I began with, and we lost 0.038. So at equilibrium, there's going to be 0.012 molarity of the ammonia remaining. Now that I know all three equilibrium concentrations, we just need to set up the Kc expression. Kc, the equilibrium constant. We know that we look at the balanced equation and we look at the products, the things on the right, they're going to go in the numerator. Only gases and aqueous species are ever included in the Kc expression because their concentrations can change during a reaction. Solids and liquids are always left out of the Kc expression because their concentrations don't change. 1 liter of water, liquid water, has the same concentration as 500 milliliters of liquid water at a given temperature. So liquids and solids concentrations are constant. They're never included in the Kc expression. So we put the product concentrations on the top. When there's more than one, you multiply them, so concentration of nitrogen times the concentration of hydrogen. And then we look at the coefficients. They were 1 and 3, so the nitrogen will be raised to the power of 1 and the hydrogen will be cubed. The coefficients in the equation become the exponents in the Kc expression. And then we divide. In this case, there's only one reactant, so divided by the concentration of the ammonia, and its coefficient was a 2, so to the power of 2 in the Kc expression. We take the equilibrium concentrations and we put them into the equilibrium expression to calculate the equilibrium constant. So that's going to be 0.019, the nitrogen, times 0.057 cubed, the hydrogen, divided by 0.012 squared, the ammonia. So the Kc will equal You might notice that I left the units out of the Kc expression. That's because when we calculate Kc's, the equilibrium constants, we don't normally include units in their values. So I'm going to ignore those units, but be sure you're using molarities in your ice table and put molarities in the Kc expression. So 0.019 times 0.057 to the power of 3, and then divide this by 0.012 squared, and we get 0.024 as the Kc value. So 0.024 is the Kc. Alright, so that was a relatively straightforward problem without any algebra in it. Now, the Kc that we have here, 0.024, is for the reaction as balanced like this. Ammonia is decomposing to make nitrogen-hydrogen, 2 to 1 to 3 the coefficients. When you balance the equation in different ways, the Kc value changes. And we remember that the two rules that we learned in class, one was that if you reversed a chemical reaction, because the products are now reactants and reactants are now products, you've reversed the equation, then the Kc expression, you need to take the reciprocal of it, because the expression is products over reactants. So when you reverse an equation, you take the reciprocal of the Kc value. The second thing we learned was when you multiply the equation by some number, suppose you multiplied everything in the equation by 3 to get a new balanced equation, then you've changed all of the coefficients, but those coefficients become the exponents in the Kc expression. So when you multiplied the equation by a number, you need to take the Kc value and raise it to the power of that number. So multiply the equation by 3, then the new Kc value will be the old Kc cubed, raised to the power of 3. So we have 0.024, the Kc for this balanced equation. We're asked to find the Kc for this balanced equation. Well, comparing this equation here to the original up above, we notice that we did not reverse it, so we don't have to worry about taking a reciprocal. But instead of 2 ammonias, there's only 1 now. Instead of 1 nitrogen, there's 1/2. So we quickly realize what we've done is we've multiplied the original equation by 1/2. Okay, it's better to express it as multiplied by 1/2 than divided by 2, just because we have that rule that when you multiply the equation by a number, Kc will be raised to the power of that number. So the new Kc value will equal the old Kc, 0.024, raised to the power of 1/2. We multiplied by 1/2, so 0.024 to the power of 1/2. Of course, to raise to the power of 1/2 means the same as square rooting. So if you want to just square root this number, you'll get the answer that I'm going to get. 0.024 to the power of 0.5, 1/2, is equal to 0.15. In the second equation down below, we've got 2 nitrogens, 6 hydrogens, and it makes 4 ammonias. Well, comparing back to the original equation, we see we've done 2 things. We've reversed the original equation. Now we have nitrogens and hydrogens as our reactants. And we took the original equation and we multiplied everything in it by 2. So we've doubled the coefficients. So we've done 2 things. We've reversed the original equation and we multiplied by 2. So it does not matter which order you deal with those, you'll get the same result. The new Kc value will be reverse the equation, so we're going to take the old Kc, 0.024, and we'll take its reciprocal, so 1 over 0.024. You multiplied by 2, so we're going to take that and square it also. So 1 divided by 0.024 squared will be the new Kc value. 1 divided by 0.024 squared gives me 1,736, or 1.7 times 10 to the 3. Okay? Now we notice one little feature there, what concept you might want to take away, thinking about when you reverse an equation, you take the reciprocal of its Kc. So when a Kc value is small, the reverse reaction will have a very large Kc. Because you take the reciprocal of a small number, you get a large number as a result. So when a forward chemical reaction has a small Kc, the reverse chemical reaction will have a large Kc, and vice versa. If the forward reaction had a large Kc, the reverse reaction will have a small Kc, because you take the reciprocal of Kc when you reverse the equation. All right. Here's a second problem. You can pause the video and try that yourself. So we have a 5-liter flask at 1100 Kelvin, that's a temperature, containing an equilibrium mixture of gases. SO3 concentration, 0.1 molar, oxygen concentration, 0.22 molar. The gases are reacting according to this chemical reaction, whose Kc value is 22.6. We're asked to calculate the concentration of SO2 in the mixture of gases. Okay, well the key, do we need an ice table for this like we used in the first problem? The answer is no, because everything in this question is given at equilibrium. This is an equilibrium mixture of gases. We're not given any of the initial conditions and the equilibrium. We're only given equilibrium concentration. So the ice table is really not necessary. All I'm going to do here is write the Kc expression for my reaction. Of the 3 concentrations in the Kc expression, we know 2 of them already. So we're just going to do some algebra to calculate the 3rd concentration. So the Kc value is equal to concentration of the products, SO2 squared times oxygen, divided by concentration of reactants, SO3 squared. SO3 concentration squared. Make sure you're putting the squared outside the brackets. We know everything in here except the SO2 concentration, so we're just going to substitute to get what we want. I like to do algebra before I do any substitution, so concentration of SO2 squared, if I solve for that, it's going to equal the Kc value times the concentration of SO3 squared divided by the concentration of oxygen. So now I'll put those numbers in. It's going to equal 22.6 times the SO3 0.100 molarity squared, and then divided by the oxygen 0.220 molarity. So the SO2 concentration squared will equal 22.6 times 0.1 squared, and divided by 0.22, we get 1.03, keeping 3 significant digits. Now that is the concentration of SO2 squared. So to get the concentration of SO2, we need to take the square root of that answer. The square root of 1.03, which is going to be pretty much the same number. So raised to the power of 0.5, or square root it, same idea. We get 1.01. And it's a concentration, so molarity. You don't need to put any units in for Kc's, but of course this was a concentration, so be sure you put the units beside it. It's a molarity. All right, the next question is just practice writing Kc expressions. However, you'll notice here there's both homogeneous equilibria and we see also there heterogeneous equilibria. Heterogeneous equilibria are where there are solids and liquids and gases. There's more than one phase present in the equation. And remember that we just mentioned earlier, you don't include solids and liquids when you're writing a Kc expression. So for the first one, Kc will equal, we look at the products and we notice this is a solid. Because it's a solid, I'm going to omit it from the expression. So the only product there that gets included is the water. It's raised to the power of 1. Its coefficient is a 1. Divided by, looking at these two reactants, they're both gases. So they both get included. So the concentration of ammonia squared times the concentration of carbon dioxide to the power of 1. The coefficients become the exponents. In the second case, Kc will equal, these are all gases, so this is not heterogeneous, this is a homogeneous equilibrium. They're all the same phase, so we're going to include all of those gases in the Kc expression. So on the numerator we have NCl3 to the power of 2 concentration. On the denominator we have nitrogen concentration and chlorine's concentration cubed. Products on top, reactants on the bottom. When there's more than one reactant or more than one product, you multiply their concentrations, and the exponents come from the coefficients in the balanced equation. In the third example, we have a small problem in that the products here are only solids. There's no gases, there's no aqueous species, there's only a solid. But solids and liquids are not supposed to be included in the expression. Because there's nothing in the numerator for this expression, there's nothing on the product side to include, we're going to put a 1 there as a placeholder. Okay, so you have to put something in your numerator, so we'll put a 1. There's no concentrations to include, so just put a 1. Divided by concentration of oxygen, it's a gas, cubed, and then the KCl is a solid, so we leave it out. There's the Kc expression, the reciprocal of oxygen's concentration, cubed. All right, question number 4. Go ahead, pause the video and give that a try. So we have a 500 milliliter flask, that milliliter. Okay, we're not going to get tricked by that. We divide the 500 by 1,000, or we set up a unit multiplier as 1,000 milliliters in 1 liter, and we know that that's 0.5000 liters. Okay, it's got this many moles of COCl2. It's set up with that many moles. So set up with, this must be the initial conditions in the flask. When equilibrium is reached, all right, so we're no longer talking about the initial conditions. When equilibrium was reached, 8% of the COCl2 had decomposed. 8% had decomposed. If that's how much decomposed, that's how much reacted, then this was going to be the change in the reaction. Okay, the change. If it had said 8% of the COCl2 is left, or 8% remains at equilibrium, then it would have been the equilibrium concentration in my ice table. So because we have the initial conditions and equilibrium, we're setting up the ice table. We know we're going to need the C equals N over V formula, so concentration of COCl2 will equal moles divided by volume. So we have 0.020 moles, we have 0.5000 liters. To divide by 0.5 is the same as timesing by 2, so this is going to be 0.040 molarity. We keep just 2 sig figs because of the numerator there. Nothing else was put in the container, so those are 0. 8% of the COCl2 decomposed. So what I need to do is take 8% of this initial amount. So 8%, 8.0 divided by 100, of times the original amount, 0.040 molarity. This is going to be how much decomposed. So 8 divided by 100, 8%, times the original amount, 0.04, so 0.003 is what decomposed. So So minus 0.0032 actually is what the calculator said. That's how much decomposed, so it's how much I'm losing. It's the change in my table. In this equation, everything is a 1-to-1 ratio, so these guys are going to gain. They're on the other side of the equation. They're also starting with nothing, so they have to gain. They're going to gain the same amount, 1-to-1 ratios. On my calculator, 0.040 minus 0.0032 is this number 0.0368. Now technically when you're subtracting or adding like this, you round off your answer based on the number of decimal places in the numbers. So because this guy has 3 decimals and this guy has 4 decimals, I'm only going to keep 3 decimal places in the answer. So 0.0368 I'm going to round off to 0.037 molarity, 3 decimal places. Now if you kept 0.0368, you have an extra decimal place. That's probably fine on my test. If you're within 1 digit of what you should have, you're good. So these two guys started with nothing and gained 0.0032, so they've each got 0.0032 molarity. Now we're trying to find the Kc values, so we should write the Kc expression. Concentration of CO times concentration of Cl2 divided by concentration of CoCl2, and we have to use the equilibrium concentrations, so 0.0032 times 0.0032, or we can just write squared, and then divided by 0.037. Again, when you're finding a Kc value, there are no units in the Kc, so as long as you're using molarities in the expression, you know you're going to be good. So 0.0032 squared, and then divided by 0.037 gives me a small answer, 2.8 times 10 to the minus 4. Of course, you don't have to write it in scientific notation. You could write 0.00028 if you prefer. Alright, so that was a relatively straightforward Kc expression, but equilibrium problem, but this one involved percentages. Okay, go ahead and pause the video and try this problem. So this question says HBr, 2 moles, is placed into a 5-liter flask. Placed into, so that's the initial conditions. Moles and volume, so we know we're going to use that C equals N over V formula again. What mass, okay, grams of bromine will be present at equilibrium? So I have the initial conditions. I'm trying to figure out something about equilibrium conditions, so that's a clue that we should set up the ice table. So 2 HBRs, this is a homogeneous equilibrium. Everything is gas and is going to be included in our expression. So let's see, concentration of HBr, the initial concentration, is moles over volume. 2.00 moles divided by 5.00 liters is going to be 0.400 molarity. That's the initial concentration of the HBr. These two were not placed in the container, so they start with nothing. Now, we notice in this problem that there's no other numbers that were given. We're not given anything else that can be put in the ice table. But we were given at the top, we glossed over that, we were given the Kc value. So we know that the Kc, in the previous questions we were calculating the Kc. This time we're given the Kc, so 0.066 has to equal the concentration of hydrogen times the concentration of bromine divided by the HBr concentration squared at equilibrium. But there's no other numbers to put in. We don't know any equilibrium amounts. We don't know anything about percentages. So what do we do here? Well, the first thing I'll notice on the change line of the ice table is that because the two products were beginning with 0 concentration, they have to increase. You can't decrease if you begin with nothing. Since those products are increasing, the reactants here must be decreasing. But I don't know how much they gain or lose. When you don't know anything else for the table except the initial line, that's the clue to use algebra in the answer. Because the coefficient of HBr is a 2, I'm going to let it lose on its change line 2x. Okay, I don't know how much, but I'll say it loses 2x. Now I can use the ratios 2 to 1 to say that this guy will gain half as much, so he gains just x. And this guy, the same ratio, so it also gains just x. At equilibrium, you have 0.400 that you began with, take away the 2x that you lost of the HBr. You have 0 plus x, so we have x and x, the concentrations of the hydrogen and bromine at equilibrium. Now I filled this table in with x's. This suggests we're going to do some algebra, so that means we need to set up an equation. Well, the equation is the equilibrium expression that we've already got here. So I'm going to take the x's and this binomial concentration and plug them into the expression here. So we get 0.066 is equal to x times x, hydrogen times bromine. I'll just write x squared for that, divided by, I'm going to put this in brackets because it's got two terms, 0.400, take away 2x, but the HBr concentration had to be squared, so we'll put a squared symbol outside those brackets. So now we've got an algebraic equation we have to solve. Now we look here and we notice that there's a squared on the top and a squared on the bottom. If we were brave to square this binomial expression in the denominator, our math training tells us that that's going to lead to a trinomial expression with x squareds in it, x's, and constant numbers, and then multiplying the 0.066 by that trinomial, we would end up being able to get a quadratic equation with x squareds, etc., equal to 0. And then if we were brave, we could use the quadratic equation to solve it. That's a lot of work. But we have a bit of a shortcut, a way to get around that, because the numerator and denominator are both squared. What we can do, if we don't have a graphing calculator, is we can square root both sides of the equation to get rid of those squareds. So when I square root, you have to square root both sides, including the 0.066. So 0.066 square rooted means the same as raised to the power of 0.5. If you prefer to use the square root symbol on your calculator, that's under the math menu. Actually, nope, it is there, but it's right above the x squared button on the calculator. So there's the square root of 0.066. We get 0.26. Keeping two significant digits. 0.26 will equal x over 0.400 minus 2x. Okay, square rooting removes the squareds on the top and bottom. Now we still have some algebra, but it's no longer a quadratic equation, it's a linear equation. There's nothing being squared here. So I'll take the number out front and I'm going to multiply by the denominator. So 0.26 times the denominator, 0.400 minus 2x, that will equal the numerator, x. Multiplying through my brackets like that, 0.26 times 0.4 gives me 0.104. I'll keep extra digits here. 0.104. Take away 0.26 times 2 will be 0.52 x's, and then that equals 1x. I'll collect all my x's on the right-hand side, so 0.104 will equal 1x plus 0.52, so 1.52 x's, and then dividing both sides by 1.52 will give me x. So x is equal to 0.104 divided by 1.52, and I remember I was only supposed to keep two significant digits in this answer, so I'll write 0.068 is the value for x. Now, if you have a graphing calculator like I've got here, TI-83, TI-84, we can solve the equation using the solver feature on the calculator. If you own a Casio calculator or some other graphing calculator, you'll have to find out the steps to do what I'm going to do here. So I'm going to take my calculator and I'm going to press the math button, math, and then of those options, I'm going to scroll down until it says numeric solver. It may just say solver. Okay, now I've got a newer TI-84, and it's got two boxes, one for an equation 1 and one for an equation 2. In my equation that I'm trying to solve, what we're going to do is let this number, 0.066, be equation number 1, and this algebra over here, it'll be equation number 2. So I'm going to set that up as equation 1 is 0.066, and I'll go to the next box. Equation 2, let me clear that, will be the algebra that I have here. So it'll equal x squared divided by brackets, make sure you're using brackets, 0.4 take away 2x, close bracket, squared. So on the left of my equation, that'll be equation 1, and on the right of the equation, that's equation 2. You press OK, and now here's something a little bit peculiar on the graphing calculator solver. Where it's flashing x equals, it's got a number there. That number is just the answer to an earlier equation that I had solved. What I need to do is tell the calculator a guess. I have to give it a number as a guess of the answer, and what it's going to do is find the answer to the equation closest to the guess that I give it. Now, that sounds mysterious, but in chemistry, almost all of our answers are small positive numbers. So I'm going to let the guess be 0. X equals 0 is my guess. I'm saying find me the answer closest to 0. Now to solve the equation, you just have to press solve, or on your calculator, you can go alpha, and then right above the enter button it says solve. So alpha solve, and we get that x is 0.06788, or x equals 0.068, which is the same answer that we got using the algebra down below. Now some of you have an older TI-83, TI-84. Let me just quickly see if I can show you how to use its solver. So when you press the math button on your older calculators, you scroll down and you find solver or numeric solver. If you've used it before, you'll get something like this with algebra up above and then this information here. Just press the up arrow and you get this, equation solver, and it's got an old equation, the equation that I just solved, and just clear it to get rid of whatever equation was there. So this is the starting point in the older equation solver. The weird thing about it was that it wanted the equation typed in the form 0 equals. But we were solving the equation 0.066 equals. Well, we can make our equation become 0 equals if we just move the Kc value to the right-hand side. So what we'll do is we'll have 0 equals all of this algebra, take away 0.066. So that's what I'm going to type on the calculator. X squared, so x squared divided by brackets 0.4 minus 2x, close bracket, squared, then subtract the Kc value, which was 0.066, right? Press enter, and we get to the screen. At the top is the equation that I'm solving. In the middle is, again, it wants me to give it a guess. And so the guess that we'll always use is that x is 0. So we're saying find the answer closest to 0. And then alpha and enter, we get the same answer, x is 0.068. Okay, so for me on one of my tests, if you don't have a graphing calculator, then I expect to see this algebra worked out. If you do, you would set up your Kc expression and then just tell me from the solver x equals. You do have to say from the solver or just solver, something like that. That's instead of doing the algebra. Alright, so we're almost done the question. We were trying to find the mass of bromine at equilibrium. We know that x is equal to this. We look at our ice table. X is the concentration of bromine at equilibrium. So this is its concentration at equilibrium. What I want is the mass. So we can do two things. We can either use the formulas, C equals N over V. We would know the concentration and the volume, so multiplying those will give me the moles. Then moles is equal to mass divided by molar mass. We would take the moles and times by the molar mass to get the mass of bromine. Alternatively, we could set up unit multipliers to do this. We'll start with the volume, 5.00 liters. I'll use the concentration as a unit multiplier to switch liters to moles of bromine. When we say 0.068 molarity, we mean 0.068 moles per liter. And then we can switch moles of bromine, Br2, to grams of bromine, Br2, using its molar mass from a periodic table. So on the periodic table, 79.9 is bromine's molar mass, times 2, because it's Br2, so 159.8 grams of bromine per mole. So 5 times 0.068. For those of you using formulas, you're taking C times V to get moles. Then multiply that answer by your molar mass, so times by 159.8, and we get an answer of 54.3 grams, or I guess we should have kept just 2 sig figs, so we get 54 grams of bromine at equilibrium. Alright, so you can see that's a more complicated equilibrium problem involving algebra, but I would say it's a fair, relatively straightforward equilibrium problem that you might see on a test or an exam. It's got this little bit of sort of grade 11 chemistry calculations at the end, switching molarity back to grams. That's a bit irritating, but otherwise it's a relatively straightforward algebra equilibrium problem. The last problem we'll look at, pause your video and try that one. Okay, so you can see here what makes this problem a little bit different than the ones we've done before is that the person setting up this experiment, they've got nitrogen and oxygen reacting to make NO, but they've set up their flask with all 3 gases in the container. So if you imagine an ice table, we're going to set one up for part B, we would know the initial concentration of each gas, and none of them will be 0. When none of the concentrations in the ice table starts off as 0, we have a bit of a problem in filling in an ice table. We don't know which concentrations are gaining and which are losing. When there's a 0, we know it has to gain. But if there are no zeros, then how do I know whether the reaction's going forwards, the products are going to increase, or whether it's going backwards and the reactants will increase? To find out, what we're going to do is answer the question part A, what direction does the reaction proceed to reach equilibrium? We're going to calculate the reaction quotient. The reaction quotient is given the symbol Q, and it's calculated the same way as Kc. So in this case, NO concentration squared. These are all gases, so they all get included. Nitrogen times oxygen. But unlike the Kc, where you have to use equilibrium concentrations, in the reaction quotient we can put in these initial concentrations. So looking back up at these numbers, we've got 3 moles and a volume of 10 liters. So we know that we're going to use C equals N over V to convert moles to concentrations. I'm going to be a little bit lazy and not show my work for that. We're just taking these 3 moles and dividing each of them by 10 liters to get concentrations. So the NO's concentration will end up being 0.1 divided by 10, 0.0100 molarity, squared, divided by the nitrogen, 0.5 divided by 10, 0.0500 molarity, and the oxygen concentration, 0.2 divided by 10, 0.0200. So grabbing my calculator, 0.01 squared, and then divided by 0.05, and then also divided by 0.02. Okay, divide twice to get the correct answer, and you get 0.1 as the value of the reaction quotient. Now, there's no units for Q, just like there's no units for Kc. Now, what does that tell me? Well, we look up at the Kc value, and we notice the Kc was 6.25. So what we can conclude here is that Q, 0.1, is less than Kc. Now, we've memorized what to do in this case, but let me just remind you of why it works. If Q is too small, Q is less than Kc, then we know that this reaction right now is not at equilibrium. And not only that, but Q, if it's smaller than K, Q will have to get bigger. Well, how can a fraction get bigger? The answer is you'll need a bigger numerator, so we're going to need more NO, and we'll need a smaller denominator, so we'll need less N2 and O2. If you have more NO and less N2 and O2, then this ratio will get bigger. So when Q is less than K, you need more products and less reactants. That means more products. We have a forward shift in the reaction. So the reaction shifts forwards to reach equilibrium. Practically speaking, that means in my ice table, the NO will increase in concentration while the N2 and the O2 will decrease. So calculating Q is telling me what to do in the ice table that I'm about to set up. So how many moles of NO are left at equilibrium? We're going to set up the ice table and solve this problem. So the initial conditions were 0.05 molarity, 0.02 molarity, and 0.01 molarity. We've decided that we're shifting in the forward direction, so these two will decrease and this will increase. If we had shifted in reverse reaction, because Q is bigger than Kc, then the left side would gain and the right side would lose. We don't know how much anything's going to lose or gain. There's no other numbers given. So just like the previous question, that's the signal to use algebra in the ice table. So I'll let this guy lose x because its coefficient was a 1. It'll lose just 1x. This guy will lose the same amount because the ratio is 1 to 1. But this guy will gain twice as much because of the 2 to 1 ratio. So at equilibrium, we have 0.0500 minus x, 0.0200 minus x, and 0.0100 plus 2x. Now we'll put this into the Kc expression. I've already written the expression up above when I found Q, so I'll just go ahead and substitute. Kc is 6.25. We see that at the top there, 6.25. So putting these concentrations in, we get 0.0100 plus 2x. That entire bracket has to be squared, concentration of NO squared, divided by the 0.0500 minus x times 0.0200 minus x. And as I see this right now, I realize that I've chosen numbers here a little bit carelessly because this is working out to a situation where if you don't have a graphing calculator, this is really going to be nasty to solve. What I should have done when I set up my problem was to make these two concentrations the same. That way, this denominator, we could write something squared on the bottom, and then we could square root both sides of the equation just like we did earlier. Unfortunately, I didn't do that, so if you don't have a graphic calculator, you should basically just pause. The only way to do this now would be to multiply the denominators, these two brackets together. That's going to give you a trinomial expression. Then multiply the 6.25 by the denominator. It'll equal this numerator squared. Oh, it's going to be messy and ugly. You're going to need to use your quadratic equation to solve that. So rather than doing all that, I'm going to use the solver, the graphing calculator solver, to do that. Okay, so this is one reason to use the solver, because it means that as a teacher, I don't need to worry about making sure that my numbers are always working out, that they are nice to solve using algebra. It means I can give you real kind of problems that you can solve using technology. Alright, so using the solver, okay, I'm going to type that in on my graphic calculator. So I've got math, and then I go down to the solver feature, the numeric solver in this case. I've switched back to the newer equation solver with the two boxes. So equation 1 will be the left-hand side of my equation, so in this case 6.25. And equation 2 will be the right-hand side of the equation, all of that algebra. Now type it in carefully. Bracket 0.01 plus 2x, close bracket, squared, and then divide. Now we have two brackets on the bottom. So what I'm going to do is divide by the first bracket, and they're multiplying. So I'm going to then divide by a second. That dividing twice works because they're being multiplied together on the bottom of that fraction. So divided by, open a bracket, 0.05 minus x, close the bracket, and then divide again by the other bracket, 0.02 minus x. There we go. Press enter, and then let's use 0 again as our guess that x is close to 0, and then alpha solve, and there's our answer. Rather than doing all of that algebra and quadratic equation, we find that x is 0.01, I guess I can keep 3 digits, so 0.0138 molarity. Alright. So now what were we trying to find? How many moles of NO will be left at equilibrium? So we look at NO, and we can say the concentration of NO at equilibrium is equal to 0.0100 plus 2x. So 0.0100 plus 2 times 0.0138, 2x. So the concentration of NO will be, get out of the solver, second function quit to get out of the solver. So 0.01 plus 2 times x, 2 times 0.0138 gives me 0.0376, 0.0376 molarity. But we wanted moles. So finally we can use a unit multiplier, or we can use the formula. I used a unit multiplier earlier, so this time I'll use the formula. If you're going to use the unit multiplier, start with your volume, 10 liters, and then use the molarity as a unit multiplier. There's this many moles per liter. What I'll do is I'll use the formula. Moles is equal to concentration times volume. So 0.0376 molarity times 10.0 liters is 0.376 moles of NO at equilibrium. Alright, so that question worked out a little bit nasty because I didn't choose the numbers carefully enough to let you do the algebra easily by hand. On a test or an exam, that would not happen. On a test or exam, you should always end up in these problems with a contrived something squared divided by something squared, so that you can easily square root both sides to go on and find x. If you own a graphing calculator, as you see, the complexity of the algebra doesn't bother you because the calculator is doing the work for you. All right, so there's a bunch of problems ranging in difficulty from pretty easy to pretty complicated algebra-style problems. And this last one we used the reaction quotient as well. These examples encompass pretty much all the different types of questions you'd see in the equilibrium unit in our grade 12 chemistry class.